Well, chemistry, we're looking at equilibrium reactions. Yay! What are equilibrium reactions? We did cover these last year, but it was during the shutdown, so who knows if we recall. Equilibrium reactions are defined as chemical reactions with opposite reaction occurring at equal rates. So we have both reactants and products at the end of the day. So at the end of the day, you're going to have some reactants, we're going to have some products left. Now, there's two different ways that we can find that. Either we call the equilibrium product constant for concentration using concentrations, where we take the coefficients and use those as subscripts, or the equilibrium product constants for pressures, where we take the pressures and use those at coefficients as exponents. Now, the most important reaction when we did focus on last year was the Haber reaction. It was the first reaction in equilibrium ever discovered, identified by a German scientist named Haber. And of course, if we balance the determine the equilibrium product constant for reaction with a pressure of 1.225 atmosphere nitrogen, 3.667 atmospheres of hydrogen, and 0.8996 atmospheres of ammonia. There's our reaction imbalance. We have it like that. So if we're going to apply for pressure, pressure is going to equal the pressure of ammonia over the pressure of nitrogen and hydrogen. But we're going to square the ammonia and we're going to cube the hydrogen from the coefficients. Put our values in. So we get 0.8996 squared divided by 1.225 equal divided by 3.667 cubed. And we get an answer of 0.0134. You'll see there's no units here. Equilibrium product constants do not have any units. Yay! Now, if the Kc is less than 1, we talked about this last year, but just reiterate it, that means the reactants favor the equilibrium. So we have more reactants than products when we get done with the reaction. If the Kc is greater than 1, then it's a product favoring equilibrium, and one has more products and reactants. Okay, so a little derivation here. Take our ideal gas equation, PV equals nRT. If we divide both sides by V, we get nRT over V. We can move that V over, and N is in moles, V is in liters, moles per liter. Remember, that's molarity. And since Kc is expressed in molarity, we can get an equality between Kp and Kc that equals Kp is equal to Kc times RT, the delta N, where the delta N is the coefficients, exponents subtracted through. We'll look at problems to show you what I mean. So for the equilibrium reactants of nitrogen dioxide and chlorine to nitrogen chloride and oxygen, determine the equilibrium product constant for concentration. If the pressures of gas at 31.98 degrees Celsius are as follows: 0.9885 atmospheres NO2, 0.8677 atmospheres CL2, 0.1223 atmospheres NCl3, and 0.09876 atmosphere oxygen. So here's our balanced equation. Here it is balanced. If we're doing pressures, we're going to put pressures of NCl3 squared, pressure of oxygen squared, pressure all over pressure of NO2 squared, and pressure of Cl2 cubed. All right, put our values in. 0.1223 squared times 0.09876 squared divided by 0.9885 squared and 0.8766 cubed. We get 0.0001943, but that's not what I asked for. I asked for Kc for concentrations. So if Kp equals Kc times RT raised to the delta N, then Kc is a Kp divided by RT to the delta N. So we know Kp, and the RT, R in pressure in atmospheres, so R is 0.0821 liters atmospheres per mole Kelvin, and temperature has to be in Kelvin, so that's 304.98 Kelvin. Now how do we get this delta N? So let's sum our coefficients in the numerator. 2 and 2, that's 4. Sum our numbers in the denominator. 2 and 3, that's 5. When we divide exponents, we subtract them. So 4 divided by 5, or 4 minus 5, we get minus 1. So we take our delta N as being equal to negative 1. So we take 0.001943 divided by the quantity 0.0821 times 304.98 raised to minus 1. and we get 0.004865. That's what the Kc is when the Kp is that value. All right, Cobb's one, we'll do this in class. Determine the equal pressure in kilopascals for the Haber reaction. And the concentration of nitrogen is 0.1122 molar. Concentration of hydrogen is 0.3366 molar. And the remaining concentration at 22.35 degrees Celsius is 0.03339 molar. That's it. Take care. Be good. Bye.